example 8 on the next page, you're now thinking backwards. This time, this is f prime. And what we want to do is sketch the graph of f. So we want to work backwards a little bit here. And then we also want to sketch the graph of f double prime, which is that forward thinking that we were just practicing. You might even want to do f double prime first. But go ahead, pause the video, and give this a shot. Okay, welcome back. So I'm going to maybe do the second derivative first, just because we've been kind of practicing how to look at that graph and take a derivative and visualize what the derivative graph would look like, where I would have a slope of 0 on f prime, f double prime would have a height of 0. And this is a relative min. So f double prime of x should change from negative to positive. What does that slope look like? I don't know. I'm not too worried about it. I need to be below and then above. That's what's clear to me. And also, since this appears to be a quadratic, the derivative of a quadratic would be linear. So I should have a line here because of the power rule. Now, doing f, I want to shift the way I'm viewing this. I'm looking at the derivative and trying to work backwards. So keep in mind, if I started off with something that was a quadratic and that was the derivative, hopefully it makes sense to you that before that must have been some type of cubic, so that when we did the power rule, I could get down here. Now, what was that coefficient? I don't know, it doesn't really matter. But I'm expecting that this should look like some type of cubic function when I'm done graphing f. Also, when you're looking at the graph of a derivative, remember that anytime you cross the x-axis, that is some type of extrema. So this, right here at -5, I'm crossing the x-axis, and the derivative has a change from positive to negative. So I've got some type of relative max right here. And then over on this portion, the derivative graph, first derivative is changing from negative to positive. So f would have a relative min. Now, how deep down does the min go? I don't know. It doesn't really matter. But what needs to be clear is that the minimum needs to be happening at the same spot that we are crossing the x-axis for the first derivative graph and having that sign change from negative to positive. Now, as I kind of go through these turning points here of these relative extrema, we are going to have a concavity change. And that concavity change should occur where the first derivative has a point of inflection, because where the first derivative has a point of inflection, has an extrema. Where the first derivative has an extrema is a point of inflection for f. So I would like it to appear to have a concavity change on f right at the same x-coordinate as where f prime has a point of inflection. Example 9 is another one I'd like you to just pause and to evaluate each statement below as true or false. We are going to have some approximate values here because the scale isn't precise enough. And when you're ready, go ahead and restart this. I'm going to add in an explanation for each of these as well, rather than just saying true or false. So for, maybe I'll even look at this first. Be careful, this is a second derivative graph. We can find less information from a second derivative graph. A second derivative graph is going to tell us two main things. It can tell us the concavity based on the sign of the second derivative. It'll tell us the concavity, oops, did that backwards, of f. And if the second derivative has a sign change, it'll tell us that there's a point of inflection. And pretty much that's it. That's really all the second derivative graph is going to be able to give us a lot of information on. We might be able to find a little bit more information, but a little bit tricky to tell. Okay, so the second derivative has a sign change, is going to be indicative of f has a point of inflection at that point. So that's what I'm looking for. Okay, so first of all, we want to find out, is there a relative max? Well, the reason that people put true here is because they see a max on the graph of f double prime. That doesn't mean there's a graph on f. So this is false. In fact, that's not even information I can gather. I can only gather information about concavity or points of inflection from this second derivative graph. And part B, f has a point of inflection at x equals 0. Close. Points of inflection can occur where the second derivative equals 0, as long as there's a sign change. There needs to be a sign change in order for them to be a point of inflection. If the second derivative touches the x-axis and bounces off, there's not a point of inflection because we didn't have that sign change. In this particular instance, f double prime stayed positive. And so we do not have a point of inflection. At around x equals 1.5, does f have a point of inflection? The answer here is true. And that is because f double prime of x changes signs. It doesn't matter if it changes signs from positive to negative or vice versa, just that it changes signs. D, f is decreasing on the interval. We don't know that, okay? We're going to put f because we cannot draw that conclusion from a second derivative graph. We don't know enough information from a second derivative graph to show that. And E, f is concave up. Well, f will be concave up where the second derivative is greater than 0. So let's just see if we are above the x-axis here. We're going from negative infinity to 1.5. And yes, indeed, f double prime is above the x-axis. So this is a true statement. Example 10. We're looking at the graph of h prime of x. We want to decide which option below could be the graph of h. So be careful every time we're switching from, sometimes we're looking at a first derivative graph, sometimes at a second derivative graph, sometimes the graph of the function. So in this instance, we are looking at the graph of h prime. Go ahead and pause the video, and this is multiple choice. When you're ready, restart it. So for this particular function right here, a derivative graph, remember that there are significant things we can pull from the graph of a derivative. Every time we cross the x-axis, it's a specific type of relative extrema. If we cross from negative to positive, this is a min. If we cross from positive to negative, there is a max right here. And when you cross from negative to positive, there's another min. So first of all, I'll just examine my extrema. I should have a min, and then a max, and then a min as I go from left to right. A has a min, a max, and a min. B, unfortunately, has that backwards, so it is not B. It is not C. And actually, that was pretty helpful. It was not D as well. There are some other things I could have gathered from this graph if there had been more than one answer that was close. Each extrema of f prime is a point of inflection, so I should be able to see a point of inflection at x equals -1, where there's a concavity change, and indeed I'm going from concave up and switching to concave down. And another when x is close to +2. And yeah, there it is. Also, if I felt like I needed more information, wherever h prime is negative, I should start decreasing, switch to increasing, stay increasing until I get to x is 0, at which case I'm now having a negative sign for the first derivative, so I am decreasing until I get up to, looks like right around 3 for x, and then I switch to increasing. And that's what really gives me those turning points for those extrema. And that's the end of our video for graph analysis, graph interpretation, day 2.